All right, so we're back at it again with an idea that Professor Snowyink gave after I submitted the other two videos. But basically, this is a pretty interesting solution. So in our last solution, we were able to rewrite 5,391, for example, as saying that's 5,000 plus 391, right? Another way we can write this is actually by taking off the least significant digit, 5,390 plus 1. And well, okay, so now we have this random 0 here, so we can factor out a 10 from this term, plus 1. And so now what we would have is for a 4-digit number, we have a 3-digit number, a 1-digit number, and a 10. So now what we're doing is we've defined this problem in a different way. If we wanted to rewrite this using notation, we can say that, all right, so we know 5,391 for a 4-digit number can be rewritten as the summation from I equals 0 to n minus 1, where digit 0 is the least significant digit, as 10 to the I di, right? And from there, we can rewrite that to say, we can go from 1 to n minus 1 of 10 to the I di plus 10 to the 0 digit 0, and 10 to the 0 is just 1, so we can rewrite that as just saying d0. And from here now, remember we said that the last term is always going to end with this 10, right? So we can factor out a 10. So now we can write this as 10 times I equals 1 to n minus 1 of 10 to the I minus 1 di plus digit 0. So now what we're saying is we have 10 times a number plus 1. So this is a number with n minus 1 digits, and this is a 1-digit number. And from there, we can start applying induction. How would we go about it doing the induction proof to put it in full form? Basically, you start out almost like exactly the same as last time. So once again, I establish my notation. I state what I want to show. I state what I'm doing induction on. I solve my base case the same way because it's still just as trivial. I'm still given a number and my induction hypothesis with all numbers with less than n digits, from 1 to n digits. I can rewrite, I know that the number mod 9 is the same as the sum of the digits mod 9. And then step 6, still what I want to show. But now in step 7 is when we can break down the problem a little differently. So we can start out with our given, and now we can take off the least significant digit. Now we can factor out a 10 from this term. And we can do this because now we would go from the smallest term would be 10 to the 0 again. Now we can apply the mod sum rule. Now what we can do is we can actually, this is 10 times another number, right? So we can apply the mod times rule. Now we can apply the induction hypothesis to this term because, like we talked about here, this term has n minus 1 digits. So, because now imagine if we were given 5,391, we have a 3-digit number times 10 plus 1. So we can apply the induction hypothesis to this term here, right? And now we can start simplifying. We know that 10 mod 9 equals 1, and 1 times this whole term is just this term here. So we can rewrite that as just saying, there's so many mod 9s, let's just eliminate the mod 9s. And then from here, we can apply the mod sum rule again. And then from there, we can just put this term back in the summation, and we have the full thing. And there we go, we're done. So what we can do here is we can quickly go step. And then at the end, we just draw it back to the original problem we had, which was show that it divides. So this is the same as the previous step. But yeah, so credit to Professor Snowyink. It was a pretty cool solution.